In the previous video I was talking about the algorithm presented by John Toro, which is attributed to David Gressinger and the Lexicon Company to some extent. And I mentioned some of the limitations of that algorithm, in particularly that it takes a mono input, which kind of limits its use as a room simulator in this one sense. Also, there was a kind of problem, well, the problem that would be revealed with some settings with the metallic sound, yeah. And with connection to that, I'd like to take a look at this block diagram presented by Keith Barr, who was a founder of Alesis and some other companies, and who is also known for his work in the field of digital reverberation. Digital reverberation. Very inconvenient word. Okay. So he mentioned this block diagram a couple of times in his forum posts and in this knowledge base on his spin semiconductor project. And he talks about it as a kind of a reference. Yeah, the key thing that he mentions is that this thing should be an all-pass loop, and as long as it's an all-pass loop, like, you can do a lot with this structure, put something inside of it, remove something, and so on, do like whatever you want, and in most cases you will get a nice result. Yeah, and the thing is that a lexicon algorithm that I showed in a previous video is the same thing. It's an all-pass loop, but there are some significant differences. First is that it's kind of half smaller than this one. That loop had only 4 elements, yeah, and those that loop had only 4 all-pass filters, and those 4 all-pass filters would exchange, like 2 of them would exchange their output with another 2 of them. Yeah, other than that, it's kind of the same thing. It's an all-pass loop. Yeah, this one is twice bigger than that. If you remember, I was talking about that lexicon algorithm, that it sounds best with the big delay times when that feedback is present in the impulse response. And this one is not an exception. It's the same thing, but now it's 8 all-pass filters. Yeah, well, 8 all-pass filters, even without the feedback, can create a very massive reverberation. Yeah, and this one, well, definitely it's an instrument of the one who wants to create an big ambient soundscape, and those echoey reverberation effects present in dub music and so on. Even more than that, Keith Barr also mentions the diffusers before this structure, yeah, in the same manner as it was with that lexicon algorithm. And also Keith Barr mentions that he came out with this all-pass loop after analyzing lexicon devices, and he attributes that idea to their work. Now, but the key difference and why I've chosen this example is that this thing has an input on every section. Yeah, here. So what we have: input, then an all-pass filter, then another all-pass filter, delay, output, then the feedback control. He, for some reason, called it KRT. I don't remember what it means. Yeah, reverberation time. Yeah, reverberation time control. Yeah, well, basically the feedback. Then again, this type of structure, again, we have an input, and so on and so on. So what those input give us is very important in my view. because this is what makes it a multi-channel reverberator. Basically, and Keith Parr also mentions that he likes when he takes the output from only a couple of these, not from all of them, but only from 2 of them, let's say, yeah, but sends the signals to every one of those. And he talks about that this sounds very nice. Yeah, the sound keeps coming and coming, and so on. And that's no, that effect, that nicety comes from that by sending the signal to different inputs of this structure, of this type of structures, we get different impulse responses, yeah. And they are not just different, they are kind of correlated with each other. So they have something in common, but also they have some differences. And this is how the real spaces work, yeah. Despite this is not an algorithm that behaves like a real space, yeah, it's a big all-pass loop, but it has this particular quality, which is very nice, and which even allows us to go further than naturalistic acoustics, I mean real room acoustics, and create something, well, special, yeah, something extra. So let's take a look at the source code. Should be rather simple. So I have 4 inputs, 4 input signals. Each one of them should go to corresponding input elements of the block diagram, yeah. In this case, it's an impulse plus 3 DCs, basically three zeros, yeah. If you want to send the 0 as a signal in Supercollider, you have to use DC, or you should convert the 0 to an audio signal with I do it with K to A usually. This works, yeah. Then what I do is I high pass, low pass the input signal in order, if I would need that. It's a very good thing to do, to have. Put some pre-delay here. Put delay times, in this case is just a bunch of prime numbers. And then I form okay, and then I form the delay times for the early diffusion, which happens here. As you can see, I take the source signals and then pass each one of them through the chain of all pass filters. For that, I want to have small delay times, yeah. So what I do, I use this very good remove at method for an array. What it does, it does 2 things. It removes an element from an array, so the array now, which is held by this times variable, becomes smaller by 1 element, yeah, at every iteration. And here I have, like, okay, let's say 4, yeah, 4 by 4, yeah, 4 by 4, yeah, 16, yeah, okay. Removes that element from an array and returns that element. So by one action I can assign new element that was taken from that array to the variable. So I modify this variable, yeah, as well as I modify this variable. So I do 2 things with one action, which is nice. And I choose the smallest elements from this array, yeah. So I remove smallest elements from them, from it, and pass those to diffusers, early diffusers. You might ask, why do I process zeros with all pass filters? It's just for testing, yeah. Actually, it's meant to be the 4-channel inputs, input signal, yeah. Also, you can see here L and R delay times, which I take also from the remaining array, from what will be left here after this line. Doesn't quite make sense here because I only have this one loop, but it was made for the next block, next synth which I will actually use. This one is just for the purpose of comparison, some small comparison. Yeah. What I have else? Well, I scale the delays just like I was doing it in the previous videos, and then comes the tank. Yeah. Now I realize this structure with the collect loop. I take size, which is 4 now, and make an array in which is created from 4 iterations through these several lines. We have all pass C, another all pass C, then delay, then one pole filter. Well, it wasn't here, I just added it. It's a very natural thing to add. And then the feedback control. Yeah. After doing this, running this collect loop, what I will have is the result, this last element. Yeah, I will have the result of every iteration as one element of this array of size, of this size, which is 4 now. Yeah. Then I take the last of it and put it to the local out. Yeah. Then I read that thing with the local in, yeah, and local in is added to the corresponding SRC array of inputs, which now will be diffused by these all pass filters. Yeah, but it still will be an array of 4 elements, 4 signals. Each corresponding element is added on every next iteration. Yeah, by use of this I variable. On the second iteration, this local in variable will not be this local in. Yeah, it will be this one. Yeah, because I always use that local in, I basically redefine that variable. So on every next iteration, it will be result of the previous iteration. Yeah, so this way I can like make this thing scalable. I can make this size like twice smaller or even bigger if I would ever need that, and so on. Okay, the code itself is not that scalable that much, but if you want, you can do that. Probably some operations here would have to be loopified. Nice word, loopified. I also would like to mention this thing. This is the thing that I like to use when I want to pass some data around. What I make is the routine that will take this array. Well, basically now it's concatenation of these 3 arrays. Yeah, it will take this data, and on every next method to that d times routine, yeah, it will pass the next one, the next element from array that is formed here. Yeah, so that's why here I always use just d times next, d times next. Yeah, same thing can be done with patterns. By sending the pattern as stream method, it will return the same type of routine. Well, I mean, it will return the routine that can also be acted on with this next method. Yeah, anything else? Yeah, delay times are in samples just because I wanted them to be prime numbers. It's a good idea to specify delays as prime numbers, so they will not create periodicities that will amplify each other for different delay lines. I mean, for the different delays, for different delays. Okay, so I have one loop, I have one local in. Yeah, but this thing has several inputs at different stages, and then I take those 4 outputs and assign them to the stereo outputs like this. Like first goes to left, second to right, then next one to left, next one to right, and that's basically it. Yeah, I also create a slider for every one of them, and spec for that slider, for those sliders, is bipolar, so I could also play with the polarity. Yeah, in a previous algorithm, the lexicon style algorithm, we also had it, but the outputs were arranged a bit differently. Yeah, the outputs would be taken from all the places and then delayed by some amounts, and those delays and differences in polarity would create the difference between left and right channel. Yeah, here it's a bit simpler, and it allows also to take closer at what we have at the outputs of this algorithm, this type of algorithms. Okay, now let's take a look at the impulse response, how it sounds. Everything is good. So, oh yeah. So what are we listening now is input is sent to the first section, and I listen to the outputs of first section that goes to left and second that goes to the right. This one goes to the right, yeah? You can hear because this one comes later, but we also get a feedback. Let's remove the feedback, by the way. We don't have anything, yeah? But we should actually hear. No, we shouldn't hear anything because the feedback is not at the. Yeah. Would the feedback control be here? We would listen. We would hear something. But because now I moved it here, we don't get anything. Let me show it like that. By the way. Yeah, it also would be a nice idea to look at it like this. Yeah. Okay. Yeah. So once I remove that, you hear how the impulse response kind of passes. Yeah, the delays pass from left to right. Yeah. And now when we add this feedback, we get kind of a fluctuation of the cross correlation. You see, it plays a little around. Yeah, this is a very nice quality, and how David Gressinger talks about it. It's very important in creating spaciousness. Well, you cannot argue with that. It definitely sounds nice, but there are lots of things that are still under question, probably. I hope I'm choosing the right terms now. But the thing is that it's very interesting, like how different rates and amplitudes of those fluctuations in time, how they change in time, correlates with different like musical genres and musical sound sources, aesthetics of the sound sources, because David Gressinger talks about that cross correlation fluctuation with the context of classical music and the concert halls. Yeah, here we hear that with the very non-naturally big reverberation. Yeah, we can find this type of reverberation in the big canyons or somewhere. Yeah, but it's not a concert hall. Yeah, for the concert hall, this type of reverberation wouldn't be acceptable. Yeah, but what if, for example, we would have smaller delay lines? So, good thing to have have in mind and play with, and this is one of the ways how we can play with that, by combining different outputs with each other, sending them to different channels, and if we have a need for that, delaying them with different amount of delays, so that we could play with that cross correlation fluctuation. Yeah, form that signal of the cross correlation. Yeah, this is a signal. Yeah, this one, it changes in time, so we can play with that by combining different outputs. Yeah. You see, now I listen to the first and last section, and it's even more exaggerated. Let's decrease delay times even more. Now it becomes slower. Yeah, now we decrease the rate of that fluctuation. Okay, let's talk about different inputs. This rotate procedure does rotate method does following to the array. If we have, let me show that thing. Three, yeah, this gives 0, 1, 2, 3. Yeah, if we rotate it 1, now it gives us 3, 0, 1, 2. Yeah, so it kind of rotates that thing. Yeah, and 2 gives 3, 2, 3, 0, 1, and so on. Now we send that thing to the input of the first section. Yeah, this first section, let's hear that. Yeah, now the second section. You see, not only it appears at a different position in the space, it also sounds a bit different. Yeah, another one, and the last one. This one starts with a rather diffused signal already, and then goes through this kind of same recirculation between channels. Yeah. So this is the key thing that I wanted to focus in this video with this structure. That how good is that when you have a possibility to send the signal to different inputs of the reverberator. It basically creates a possibility to position a virtual sound source in a certain spot in a virtual enclosed space. Yeah, let's call it like that, virtual space. So, but I would like to take this ability even further and create two such tanks, one for the left channel, one for the right channel, and then have 8 inputs, and that would open up even more possibilities. Like we could exchange signals between those two structures and do some other stuff. So let's take a listen at this example. Now it's same as before, but now we have 8 input channels. Now I assigned them to Sound In, which will read from other Jack clients, and Jack is the sound server that is available on Linux and other systems, but it works with Linux better, as to my knowledge, with some other systems. That's one of the reasons why I use it, why I use Linux for that stuff, because this is one of the most important things for me, ability to interconnect programs and so on. I was very much astonished back in the days when I first found this thing. At those days it was in I don't remember, 2004 to 2005. There was only a rewire thing that would connect was that Reason to Cubase. Yeah, and you could play with those two programs. Then I found this thing with Linux system, and was wow, like this thing is open source and you can just use that, but why isn't it on Windows? I was using Windows before that, and it's still probably the best thing to interconnect programs with each other, like musical programs, yeah, the sound streams. And still it works best on Linux, and on other systems people talk about some problems with that. I don't know. For me, it's the key. It's one of the most important things I want to have. Okay, now I take those L and R. That's actually why I made them like L and R parts, and I assign the inputs so that I would have 4 inputs in one tank and 4 in another one. And so with this end delay lines, now I have 2 delay lines, end delay lines loop, I take this array of nils. It's a 2-dimensional array. Every element has 4. Every array has 4 elements, and they are inside of another 2-element array. and then I fill this tank ins 2-dimensional array, with corresponding inputs. I have 8 inputs, so one input, odd numbered inputs go to one array, and correspondingly will go to one tank, and even numbered inputs will go to another one. That's the thing. Now let's listen with the real signals, real life signals. Let's launch it. Let's launch it. Here it is. Verb 1, okay. Not a problem. So, nice. This is a wingy one. I made this on purpose. What is this? Okay, let's play with this one. So level 0, 1, 2, 3 is for left channel and corresponding tank, and 1 and 10, 12 and so on are for the left. Yeah. Other than that, it should be the same as before. Yeah. So, what I wanted to show here. Let's take the first one. This one is connected here, yeah. If we connect that to another channel, to the next channel, it goes to the left one, to the right one, to the left one, and to the left one, and again and again. Yeah, so now I have some possibilities to connect that thing and even to pan between these two. Yeah, you see? So I kind of have this possibility now to place my sound source between them, and I can take another one like this. And let's do it like this. Yeah, and it feels kind of like being in the same room, yeah, but not at this certain precise point as it would be with the previous reverberator, yeah, because now this is now a different thing. It has this third channel, yeah, and these channels are not summed to mono on the input. Yeah, they are as they are 8 channels, and they go to different points in those 2 tanks. Now this one. Rather noisy sound. Okay. And another one. And let's connect it something like that. This is the 8, okay, and 9. And let's put 9 like this. So I guess you got the idea, yeah, why this is good. This is the thing that, like, for me is I see the potential, the very big potential in creating kind of alive scenes where your musical instruments, the algorithms that you design, can act as a real virtual sound sources with the more convincing sound picture than it would be with different settings for well, one input reverberator. Yeah. Although that one also has its positive sides, and I talked about them in a previous video. Yeah. Okay, now another thing that I'd like to take a look at is this ring equality. I want to mention okay, now same as with previous lexicon type design, if we remove that feedback, we hear that nasty metallic quality, and it's especially obvious when the delay lines are smaller. When they are bigger, then we can solve this problem. Yeah, the modal density now becomes the modes, the resonances now becomes lower, and we don't hear it that much. And I will talk a bit. I will go deeper on this one in the next video. But now I want to present one thing that can make things a bit better. and this is a nested all-pass filter. Nested all-pass filter is the filter which holds another all-pass like this one, but inside of this one. Yeah, so after this delay it would be another all-pass filter, and then the sound would go to the feedback and feed forward and so on. Supercollider has nested all-pass filters, by the way, but for me they don't work all the time as they should. I mean, sometimes I launch it and it just screams at me without any input signal. I don't know, maybe some instability, maybe some methods are wrong, I don't know, but that's what it is. So I made a couple of other filters. This one is a all-pass filter that I made from the from what we have in Faust library. Yeah, basically from the parts in Faust library. So here's the block diagram. I have an input signal, it then gets multiplied by G and goes to the output, and another copy of it goes through the delay that has an interpolation, then to the feedback, multiplies by minus G and goes back. That simple all-pass filter. You can see this mem here. It is how this filter is designed in a filters library of Faust, and what they do there, they remove one sample on this feedback and then add that sample later. And I guess that's because this thing would add another, without any delay, this feedback cycle would add one sample of delay, yeah. But this is still a bit unclear to me, because last time I used it, it would compensate without those additional actions for that one sample. So not that clear to me, but that's how it was present in the library. I just put this F delay here, and another thing that I did so that this would behave like an all-pass filters in Supercollider, I made this G, this coefficient of an all-pass filter, be calculated from the decay and delay times. Yeah, I was talking about that in a previous video, and also we'll talk about that in the next one. So I have it here. Yeah, there's one problem. If you want to specify delay time in samples, sorry, in seconds, yeah, you use this ma.sr. Ma is a variable, yeah, probably can be called a variable, although this is a functional language. Well, okay, let's call it a variable. But basically it's a data structure that holds elements from, it holds functions from, in this case, math library. Yeah, and they all the libraries are imported with this import std files. This std files will then do the assignments to import all our other libraries. The thing is, this value will be calculated on the runtime. Yeah, but you cannot introduce something like this, which is to be known at the runtime, to the sliders. So you have to put something literal, something that will be known at the compile time. And so when I specify this delay sec resolution for this slider, I have to hard code the sampling rate. Yeah, couldn't find any other solution yet, so that's how I did it. Well, it's enough for me because I always use this sampling rate. Don't see a reason to use bigger than that. I would use 48 probably, because, well, it seems now be better supported by the hardware. But I have a lot of stuff done for that sampling rate, so it's not that easy switch for me, and it doesn't do a big change, so not a big deal. Not a big deal in my case. Okay, here's the nested one. Yeah, this is a nested one. So the nested one is the same thing, but now after the delay I have another all pass, just the one that I showed previously. So this is it. Let's compare how they sound. The work on this all pass nested all pass filters probably should be attributed to William Gardner, who also done significant research in the digital reverberation area. Also worked with David Gressinger closely and probably at Lexicon. But he came up with his own algorithms, and those algorithms, you can find them in Supercollider's help file on nested all passes. Those algorithms would always use those nested and even double nested all pass. Double nested all pass is two all passes in chain inside of another all pass. What it does, how William Gardner puts it, it helps to grow echo density faster than with the cascade, and also it kind of helps to interrupt that. That's from my own words. Interrupt that periodicity in the sound. So this is a cascade. Hear that? And these are same with the same settings, same filters, but in a nested topology. You hear there are some interruption. There is some interruption, low frequency interruption present. Yeah, and another thing, it kind of dies out in a bit different manner, and lasts a bit longer. Yeah, so this is a different structure with different configurations for the diffusion parameter. Yeah, the decay time for the two filters. Well, you can find a bit different, probably in a lot of cases better results than with just a cascade. So with this next one, we have only one nested all-pass filter, and the same is, and the rest is the same. I would, yeah, let's put it like that. Let's put how it was. Let's put it how it was. We can also reverse this thing, so two tanks would interchange signals with each other. So you can put a ladder here. I won't waste time showing this thing now, or should I? Yeah, okay, let me show the same thing. This was a ring here. Yeah, let's show that thing. All the settings are at the same place. Yeah, have them same. Yeah, the difference is only you can hear that metal, yeah, in a cascade, but this is a bit nicer in that regard. It's like a one step further, dealing with that metallic sound. Yeah, but we're not finished. In the next video I will talk more about that. But now I'd like to take this structure and make a reverberator. Make a reverberator, by which I mean not only the tank, but also organization of how direct sound, early reflections, and the tail are organized into one system. So what I can do now with those 8 inputs is not only connect different sound sources to different inputs of the reverberator. I can now also connect different reflections of the sound source of the signal that comes out from the reflector to different inputs, and this now will not result in that combi phasey signal that we had before, that I showed before with the lexicon. And I said in that video that with that design it would be better to feed a direct sound to a tank, yeah, not the sound of the reflector, because when you send the reflector to this signal, you basically get almost same, well, yeah, almost coherent impulse responses, and you place them like one after another, and so you get a kind of a comp filter, yeah. But when you have those impulse responses decorrelated, now you don't have that problem. And so now we can take a reflector and feed that into the reverberator, and not a direct sound. So that becomes even more natural than how it was before. So what I do here, this is a reflector, this is a reverberator, the tank with its last version. This is a reflector as it was in a video on early spatial impression. If you didn't watch it, it's also an important topic. The difference is that now it has two outputs, two out unit generators. One takes the sum of all the band reflections, which are the copies of input signal with different polarities and different filter coefficients on one-pole filter, low-pass filter coefficients on each one of them, and different delays. Yeah, so those are kind of filter taps from the dry signal. So the next thing that I do, also important, I remove the initial diffusion from the tank and put it into the reflector. So now every sound source has its own small cascade of all-pass filters for its input signal, just to diffuse the sound. Yeah, and that signal is summed to stereo, pair, and sent to this output, out bus, controlled by out bus control. And another thing, another out gets, in this case I have five reflections. Where is that? 5 reflections, yeah. And these 5 go to that effect bus, 5-channel effect bus, yeah. So I just send those 5 reflections, each one to its corresponding bus. Now what I have is this wavetable synthesizer from the video on wavetable synthesis. Also, if you didn't watch it, everything is explained there. Everything about this structure. I won't dive into this now. And so I make 3 synthesizers, every one of which has a bit different timbre, controlled by this corresponding wavetable. I launch those 3. Those 3 are connected to 3 reflectors, corresponding reflectors, and those reflectors are connected to the tank, yeah. And they are connected to the tank so that each one has 5 outputs, yeah, 5 output reflections. 5 reflections are connected to 5 outputs, yeah. And I have 8 inputs in the reverberator, so I just play with it like that. The first reflector goes to 0, 1, like the first, second, and so on, buses that tank listens to. The second starts from the next one and goes till 7th, yeah, and the next one starts from the 3rd one and goes till 8th. Okay, and then what I do, since this, again, this is a very big space generator, yeah, it's not that in a lot of senses not naturalistic, yeah, it's a big echoey thing. Well, maybe we could say that it's naturalistic, but I want to take unnaturalness here further by combining this naturalistic characteristic of it with some like fantastic stuff. In particular, this fantastic stuff is expressed with changing the feedback over time and changing the diffusion over time, yeah. In real situation, we would have to basically have the space that would change its shape and internals. Usually we don't have that. Probably there are some experiments. I remember Stockhausen had some space in Japan, if I'm not mistaken, where he would put listeners on the chairs, and the musicians, that was a big circle, and the musicians would be at different places in that spheric space. There wouldn't be any reflections from the floor and so on. It would create a specific sonoric aura or something like that. And but I don't know of lots of experiments like that, and even this one is not. It's a bit different thing. Also, do I put, by the way, do I put the resonances here? I had the resonances. Oh yeah, I also put the resonance. I add the resonance to every one of these elements. I also add the resonant, a peaking filter here. And here I also play with this. Yeah, so I have a center frequency, the gain, and the Q for that peak. I play with this over time. So another thing I didn't mention is that Keith Barr also mentioned that he likes in particular when delays are organized as follows. There is one delay, then another delay, and then this delay is a little bit less than the sum of those two. Yeah, so this algorithm plays with that idea, but I also convolute that idea with another one that comes from Manfred Schroeder, who is a pioneer in digital reverberation. And his thought was that the delays should be of increasing order, yeah, increasing order of magnitude, which namely means which means like if the first one is 3000, the next one is 3 times less, then another is 3 times less, yeah, or maybe not 3 times, but order is kept, yeah. And I also like an idea when the first one is, let's say, this one, but next one is bigger, and then another one is bigger, and so on. Musically, all of them can have their context in which they will fit very nice. Again, all of this tries to make an ideal reverberator or something are kind of good scientific tasks, yeah. But in art, and that's why reverberator making usually called and half an art and half science, or half a science, half an art, because it very much depends on what is the sound source and what is the artistic context. Because some very bad sounding enclosed space in a certain context might speak better than any other one, yeah. And by the way, natural spaces are not ideal at all. None of them is ideal. They all have resonances. They all might sound awful with certain sound sources, yeah. So you never know unless you try it in a certain context, and when you have lots of it in your head, like in your memory, then you can say before you try, like in which context which one will sound nice. Okay, now let's listen to this one, what it can give us with these synthesized sounds. How can it bring some life and naturalness to the sounds, and at the same time bring something extra. Let's listen to those sounds without the reverberator and the reflector. Let's compare. Let's just take a listen at. Oh, what's wrong? Yeah, no. This, we don't need this, and we don't need this. Now, yeah, now it works. Let's listen to these delay times, fancy delay times that I made as well. This should make even bigger difference in the impulse responses. depending on at which input the signal comes. As usual, I hope this will be helpful in your sound design, and see you.